This is section 4.6. We're going to look at the trapezoidal rule. Trapezoidal rule, we talked about it before. We're trying to find the area under the curve. At least we're trying to find a approximation. And so what we're going to do, a little bit different than what we've done before. Instead of taking these subdivisions and cutting them into rectangles, like if you recall, this is the left-hand rule. This left-hand rule left a whole bunch of area that was under the curve, but we weren't using it as part of the area. So we said that this was an underestimate. Similarly, if we take the right-hand rule, if we use the right-hand rule, you'll notice that we're creating extra area that's outside of the curve, and we refer to this as an overestimate. Well, instead of doing an overestimate and an underestimate using these left and right-hand rules, what we do with trapezoidal is instead of going horizontally, we go diagonally, like this. And doing that kind of gets rid of a lot of the waste that you get from the other methods. So, in this particular problem, I'm taking the integral from 4 to 9 of the function radical x, and I'm going to use actually not 6, but 5. I'm going to use 5 trapezoids. So my trapezoids are right here. Let me draw one for you. Here's my first one. Okay, I'm going to call that trapezoid A. Here's my next one. This is my trapezoid B. Here's my next one. Here's C. Here's D. And here is E. Now I need the heights of each of these. So this is the function y equals root x. So if I start here at 4 and I plug 4 in, this height right here is root 4 or 2. I'm going to leave it as root 4. Here at 5, this is root 5. At 6, this is root 6. At 7, this is root 7. At 8, this is root 8. And at 9, this is root 9. And I'm leaving it in that format for a reason. So let's write out these areas. So 1/2 base 1 plus base 2 times the height. And the height here is this region, and it's just 1. Okay, these are all 1. Now, some of you may think, wait a minute, that doesn't look like a trapezoid. And you're right, it doesn't look like a trapezoid that way, but if I put it on its side like this, here's our trapezoid. Okay, we're calling this and this, these are my bases, here's my height. Okay, so for B, it's 1/2 root 5 plus root 6 times 1. For C, it's 1/2 root 6 plus root 7 times 1. For D, it's 1/2 root 7 plus root 8 times 1. And for E, it's 1/2 root 8 plus root 9 times 1. So those are the areas of my 5 trapezoids. Now if I wanted to find the total area, I would add these all up and that would give me the total area. But my goal here is a little different. I'm going to write these in a different way. I'm going to write them horizontally. Okay, there's A. There's B. C. There's D. And there is E. So what I notice here is that all of these have the term 1/2. And they also have the term 1. Now I'm going to factor those terms out. So I'm going to write this as 1/2 times 1. And what's left is root 4 plus root 5 plus root 5 plus root 6 plus root 6 plus root 7 plus root 7 plus root 8 plus root 8 plus root 9. Now one thing I want you to notice is that within these parentheses, I have 1 root 4, but I have 2 root 5s. I have 2 root 6s. I have 2 root 7s. I have 2 root 8s. And then I have 1 root 9. And I'm actually going to put the 1s, well, all of these, I'll put them in red. Because we're going to start to see a pattern. Do you see how it goes 1, 2, 2, 2, 2, 1? Now, 1/2. What I want you to notice about this 1, this one's kind of important for us. This one's important because the 1 comes from the following. I know that I'm going from 4 to 9 here. So I know that I'm looking at the interval 4, 9. And I know that n is equal to 5. Well, if you recall, we said that delta x was b minus a over n. Remember, this is my a, this is my b. So 9 minus 4 over 5 equals 5 over 5 equals 1. So this one here, it was easy to see from the picture, but we actually calculate that. So I'm going to write that as 9 minus 4 over 5. So you know that that is our delta x. Now within these parentheses, again, I have 1 at f of 4 in this case. And what does that mean? Well, our interval starts at 4, so 4 is the first thing that I plugged into y equals root x to get this first height. Okay, and then I have plus 2 times f of 5, that's for this one, so we did that one and that one, plus 2 times f of 6, that's this one, plus 2 times f of 7, plus 2 times f of 8, plus 1 times f of 9. Okay, so now it's 1/2 9 minus 4 over 5, 1 times f of 4. And it turns out that f of 4 can be rewritten like this. Now, where did I get these numbers from? Well, 4 is our a value. That's the start of our interval. 1 is our delta x. And it turns out that our 0 is going to serve as our counter. So when I write this whole thing out, it's actually going to go like this. 4 plus 1 times 1 plus 2 times f of 4 plus 2 times 1. Plus 2 times f of 4 plus 3 times 1 plus 2 times f of 4 plus 4 times 1 plus 1 times f of 4 plus 5 times 1. That's getting a little cramped there. But if you look inside, of here, 0 times 1 is 0 plus 4 is 4. 1 times 1 is 1 plus 4 is 5. 2 times 1 is 2 plus 4 is 6. 3 times 1 plus 4 is 7. 4 times 1 plus 4 is 8. And 5 times 1 plus 4 is 9. So we've actually accounted for all of our pieces. And so putting this all together, you have a very systematic approach as to how you can calculate numerical approximations for area under the curve using trapezoids. It turns out that the formula actually looks like this. They call this first one x sub 0. And then x sub 1 would be the next one. And we continue this pattern until we get to this one, which would be x sub n minus 1, and then this last one, which is f of x sub n. And so this rule is called the trapezoidal rule. Now, I'm not going to go through and solve this. There is a numerical value. The big thing right now is to figure out how to set up one of these problems. And I'll show you how to actually solve one in the next video.